Okay, due to that some voltage must be present here, then why I am taking this as 0? So any student get this basic doubt, that is, when definitely I am giving 10 volts, let the drop be 2 volts and I should get here 8 volts. How can I say that VB is 0? This is because that is what you need to understand. Op amp will not, we should not say op amp, we are giving input to op amp. Op amp takes the input. It is only giving back the feedback and it is only taking the value. So it will decide how much voltage it has to take from the input signal, and such that the net voltage of these two will become equal. Okay, this is the wonderful design we have in the case of op amp. Okay, so based on this principle, we call this concept here as virtual ground. Okay, that is what is the point here. Now, so this is about virtual ground concept we have in the case of a op amp. Now, you can take, most of you must have learnt about voltage follower. Okay, we'll be discussing as we move further. Now, try to see, when in a voltage follower, this is nothing but a voltage follower circuit. Okay, voltage follower circuit. In a voltage follower circuit, what you will do, suppose that if I give 10 volts here, okay, now if this is 10 and here also it is 10, therefore output voltage V output is equal to 10. So I say that V output is equal to V input in case of a voltage follower. This is what we say. Okay, now the point here is, the truth is that the op amp originally, what you give here voltage, it will take it, amplify it and give it to the output. It will bring back this voltage. In this process, okay, as this output will be in amplified form, that is 100 volts now, because if it is 100 volts, because gain is 10. Okay, if it is 100 volts, then it has to get me here 100. Okay, now it will take 100 minus 10. I am going to get this value as 90. So 100 minus 10 is equal to 90. Now this 90 it will amplify and it is supposed to get me here 10 times and get 900 volts. Okay, if you see here, this voltage is increasing. Okay, but again, it will bring back this voltage here. But as you are providing negative feedback here, okay, the value should not increase, but it should decrease. When I try to move further with other circuits, then you will understand it better, not with just only this example about negative feedback. Okay, so what happens here is that this voltage, what I am getting, every time should be reduced. Okay, every time it should be reduced because of negative feedback. When this value is reduced, obviously the signal which comes here also will be reduced. Okay, as the signal is reduced, at some point this voltage difference value will become 0. If it is not able to become 0, then we can understand that op amp has failed to make the voltage VD 0. Okay, and difference will be left out. That difference voltage only we are looking it as amplified voltage. So that is the reason we call op amp as a error amplifier. Okay, not just as a difference amplifier, you call it as a error amplifier. It amplifies the error between these two signals and gives it at the output. Okay, so the ability of this op amp to bring this voltage to this point, we are calling this here as a virtual ground concept. Now let us look at non-inverting amplifier. Now we will try to see in this order. First we will complete non-inverting, next difference amplifier, next AC-DC characteristics. In AC-DC characteristics you will get offset values, and in AC characteristics you are going to get the behavior gain frequency response of the op amp. Okay, so just pay attention in this regard. Now So let us try to take now the second one what we have taken, that is non-inverting amplifier. Yesterday we have discussed first one, that is inverting amplifier. Now we are discussing non-inverting amplifier. Non-inverting amplifier. So the non-inverting amplifier, we try to define it when the input is given to the non-inverting terminal and inverting terminal is grounded, then we say that the op amp will work as a non-inverting amplifier. So this is node VA, node VB. Okay, now I have here. Now here, assume that op amp is ideal. Okay, assume op amp is ideal. Okay, now VD will be equal to 0. Now once you try to take here, that is VD is 0, that is VA minus VB is equal to 0. Yesterday I told you what inputs you give, that op amp will not consider only the terminal voltages, it will consider it as input. Okay, that is what I say. Op amp, we should not say op amp we give input to op amp, instead we should say that op amp takes input. Okay. Now so VA minus VB. Now as VA here, that is we have now VA equal to VB. Okay, because of that I say that as VA is equal to VI. Okay, that implies VB is equal to VI. So put it this aside. Now let us write KCL at node B. KCL at node B. Now try to see here what input I give, I get amplified voltage here. Now I get here the feedback current, this is IF, and this current comes because of ideal op amp, it has got infinite input impedance. Okay, as it has got infinite input impedance, what happens is no current will enter into this, the entire current is going to come like this. So this the current we name it as I. Okay, now I have a KCL here, IF is equal to I. Now what is IF is V0 minus VB whole divided by RF, and what is I is VB minus 0 divided by R1. Okay, now I am going to get this as V output by RF is equal to V output by RF is equal to VB by R1 plus VB by RF. Okay, you will get it. So V output by RF is equal to now VB into 1 by R1 plus 1 by RF. I am going to get this now V output equal to 1 plus RF by R1 into VB. Okay, what is VB? VB is nothing but VI. So 1 plus RF by R1 times. Okay, now VI I get it here, V output. Now this is how I get this output voltage of a non-inverting amplifier, and the gain of this is given by ACL equal to V output by V input is equal to 1 plus RF divided by R1. So I get this point here like this, ACL equal to 1 plus RF by R1. So in this gain, as there is no negative sign, so there will be no phase shift in this case. What input you give in the same shape, it is going to get at the output. Okay, this is the point. This is what we understand from non-inverting amplifier. So the gain of non-inverting amplifier, if you see the formula now, because here the feedback provided here is also negative feedback only. Now you try to understand here that ACL equal to 1 plus RF by R1. 1 plus RF by R1. Now if you try to take here this point, okay, like this. Now in this case, that is whatever you see here, the formula, the gain of the op amp is not dependent on the op amp itself. Okay, it is dependent on the resistors what we connect, which provide feedback for the circuit. That is RF by R1. So this is the point we need to remember. So this is the gain of the non-inverting amplifier. Okay, fine. Now let us try to go for the next one, that is difference amplifier. These three are called basic amplifiers: inverting, non-inverting and difference amplifier. Okay, like this. I am going to erase this. Now third one, difference amplifier. Now in difference amplifier, we try to give input to both terminals, okay, at a time. So I am going to give V1 input, V2 input at a time. Now this is node VA. Let this be R2, R2 equal to R1, and let this be R3, R3 equal to RF. You should select the values like this. Now try to select it like this. Now let us see here. Now what is this circuit? Now let us try to see here. When I give both inputs at a time, I need to understand here this logic. That is, assume op amp to be ideal op amp. So if it is ideal op amp, okay, now I need to consider two inputs at a time. So that is the reason I will try to take the help of superposition theorem. Okay, now consider, or you can say apply superposition theorem. Okay, now on applying superposition theorem here, what you are going to get here is that like this, V1. Now consider V1 input only. Consider V1 input only. Okay, if you consider V1 input only, then I need to take here the circuit like this, minus plus. Okay, this is ground and this one is also grounded. That is R2 resistance, okay, and R3 resistance, both are grounded. So there is no use of this. Now I have here R1 resistance, okay, and feedback resistance here like this. V output. This is here RF, IF here and I here. Okay, now this is here V1. Okay, like this we get it here. Now try to see here. If these 2 points are grounded, then there is no supply from this point to this point. So you can understand that is VA will be 0 now. Okay, VA will be 0. So VB will exist here. Okay, now as equal to VB, because we are giving input voltage only to the inverting input terminal, non-inverting terminal is grounded. Now this circuit will work as an inverting amplifier. So without doing directly, you can put it here. That is the output of. Okay, I'll mention here like this. As now the circuit functions as now the circuit functions as inverting op amp. Now you can get it like this. Inverting op amp, you are going to get it like this. That is, V output will be equal to minus RF by R1 into V1. So yesterday we have done the derivation for inverting amplifier. So V01, that is output when given, output of op amp when input of inverting input is only considered, okay, is V01 equal to minus RF by R1 into V1. Next, so consider V2 input, consider V2 input only, okay. Then as now the circuit functions as non-inverting amplifier, non-inverting amplifier. Now you redraw the circuit, minus plus, okay. Now the inverting terminal should be grounded because only non-inverting is considered. Now the feedback current, now I current here and ground it, I get R. Now I get here this voltage like this, okay. This is R3 equal to RF and R2 equal to, okay, R1. Now I give here V2 input. Now this will be the VA voltage will be the input, VB voltage will be here. Now as the op amp is ideal, due to virtual ground, VA should be equal to VB, okay. As it is equal to VB, okay, as it is equal to VB, now you need to take here this point like this, that is VA will R. Now I get here this voltage like this, okay. This is R3 equal to RF and R2 equal to, okay, R1. Now I give here V2 input. Now this will be the VA voltage will be the input, VB voltage will be here. Now as the op amp is ideal, due to virtual ground, VA should be equal to VB, okay. As it is equal to VB, okay, as it is equal to VB, now you need to take here this point like this, that is VA will be equal to, okay, VI, voltage division rule, VA will be equal to V2 into R3 divided by R2 plus R3, which is rewritten here like this. VA will be equal to V2 into RF divided by, okay, R1 plus RF. This is the value of VA. Now the output of non-inverting amplifier, output of non-inverting amplifier. non-inverting amplifier is V output equal to 1 plus RF by R1 times, okay, V input, that is VB, due to virtual ground VB will be equal to VA, okay, VA. Now VA, if you substitute, it is 1 plus RF by R1 times, okay, into VA is, that is V2 into RF divided by R1 plus RF. Okay, now you can rewrite this, take the LCM here, you are going to get R1 plus RF by R1 into V2, okay, into RF divided by R1 plus RF. Now cancel these two terms, so you are going to get RF divided by R1, okay, V2. So this is V02, this output is V02. Now the total output, okay, output is V0 is equal to V01 plus V02. So this you will get it as, okay, that is RF minus RF by R1 into V2 plus RF by R1 into V1, okay, V2 here, V1 here. So the final output, V output will be equal to, now you take RF by R1 common, is equal to V2 minus V1. Now this is the final output. So now this circuit will work as a difference amplifier, that is, it will take the difference of two input signals, and amplify it. The amplification factor is decided by RF by R1. Okay, select RF 100 and take R10. So 100 by 10 is 10. So whatever is the difference, 10 times of that difference you will get it at the output. So this is how the circuit is going to work. So this is output of a difference amplifier. Okay, this is the output of a difference amplifier. It means it will take these two inputs what you give. I told you, it is not this input it considers. It considers only VA and VB as input. Now this is how it is going to work here. Okay. So this is what is about difference amplifier. So any of the op-amp applications you take in linear mode, that is in amplification mode or linear mode you consider, okay, then the op-amp is going to fall under, op-amp applications are going to fall under any one of the three categories, that is inverting, non-inverting or difference amplifier. Okay, any application you take, it will come under any one of these three categories. That is the reason we call them as basic op-amp amplifiers. Okay, basic op-amp amplifiers. Now here, now let us come to the practical approach towards this, okay, through which we try to study the characteristics of this op-amp. So this I have introduced before the characteristics before, because when you try to study the op-amp, what happens is, in the beginning if I tell about offset voltages, you will not be able to, okay, understand what is the importance of offset values. Now as per the rule, now everybody try to understand just now what I am telling. Okay, suppose take example here like this. Okay, take example here like this. Take RF is equal to, okay, RF is equal to 100K, okay, and R1 equal to 10K, then V output, okay, V1 is equal to 5K, 5 volts, and V2 is equal to say 10 volts, then I am supposed to get V output equal to 100K divided by 10K, okay, and 10 minus 5, okay, this I am going to get as 10 into 5 is 50, okay, 1000. Okay, this is how I am supposed to get. Okay, like this, V output I am supposed to get. Just take it as an example. Practically this values will be in microvolts. We don't take 5 volts, we take 5 millivolts or microvolts, and 10 millivolts or microvolts. So then you are going to get, okay, only hardly 5 volts, not more than that. Okay, for example, for ease, take it like this. So I am getting V output equal to here, okay, 50,000 value. Okay, right? This is how I am trying to get this value. Now, in this case, what is the point you need to observe here is that, okay, if you try to give input to the op-amp and try to study the values, you should get a reading of 50,000. But practically, you will not get the reading of 50,000. You will definitely get either, okay, error voltages. You may get more or less. You will definitely get more or less. Okay, this is because of the malfunctioning of this circuit. Okay, Why? Because it is an integrated circuit. We have determined, we have designed the circuit and fabricated it in a IC. Okay, when you fabricate it, to perform it well, it will be provided with proper biasing. How you have done in the case of transistor biasing, fixed bias, collector based bias, like that. Here also, the biasing is done inside this op-amp for the transistors properly. Even though how much properly you try to do the fabrication and manufacturing, okay, some small errors will creep into this manufacturing process, or due to the transistor beta factors or transistor AC factors, that is HIE, HFE, such kind of things. Okay, due to those errors, we will have some effects on performance of this, and this output will not be expected value. Either it will be more or less. Okay, now if it is more, then also it is error. If it is less, then also it is error, because it should match our mathematical calculation what we have done here. Okay, so then only we say the output is distortionless output or faithful output. So because why that error comes is because of offset values. We have studied one characteristic in the ideal conditions, that is zero offset voltage. It means when I don't give any input, I should get output voltage 0. Okay, if you are getting more or less voltage, means definitely there must be some offset error in this value. Without our permission, somewhere we are getting voltage in this entire circuit of op-amp. So that we have to identify that error and eliminate it. So that's the reason we try to study these errors. Now, so how we have done biasing, fixed bias, collector based bias, voltage divider bias, like that it is not possible to study here. Anything what you want to do, you can do it only outside the IC. You cannot go inside the IC. Why? Because it is fabricated once. Okay, you will not have an option to interfere inside the transistor operations. So then, as we have no operations to deal with the IC which is inside operations, so only thing what we can do is from outside only we can deal the op-amp. Okay, so they very well know that definitely there will be some errors. That is the reason wantedly they have put one pin called offset. Okay, offset pin. Pin number 5 we have as a offset pin. So definitely you should know about this part. So in order to handle this, let us see here once this configuration. So now that you have seen the amplifiers, and just now why we study the DC characteristics here is, earlier DC characteristics studied in transistor, is for biasing. Okay, but here the biasing job is done by the manufacturer itself. He provides all the internal connections and biasing is perfect. Only if you provide VCC, automatically the transistors are biased and you will get faithful results. But when you get error, what to do? That error job, why you are getting it, that correction only is about offset values. So that is the reason we should study about DC characteristics of this op-amp and AC characteristics of this op-amp. If I give AC characteristics to a BJT, I call it that as nothing but H parameter analysis. Here also we should study like that, but you don't have any H parameters here. Why? Because you are dealing the device with outside the op-amp, not inside. Okay, now let us see here. So put the heading there. Now here, DC characteristics. That is fourth topic what we have, DC characteristics. So these DC characteristics are about, offset values only, not about anything else. Okay, why? Because we have nothing to do with biasing here. That the designer has taken care of it. Okay, only thing is whether you are getting proper output for a given biasing or not, you should check. If you are not getting it, you have to correct. So what should I correct? That is the question. For that, there are some parameters to be observed here. Let us try to see. Now the first one what we have is input offset voltage. Input offset voltage. And second one, output offset voltage. Output offset voltage. Third one. Okay. Output offset voltage. And you have, let me right, okay. Input offset current. Input offset current. And fourth one is you have input bias current. Input bias current. Okay. Now here like this. Now let us see here first these three and last we come to this. Okay. Now let us see here first this one. Input offset voltage. That is the op amp which is designed, okay, is like this. It has got two inputs, V1, V2. It has got two inputs, V1 and V2. Now, when this V1 is grounded and this V2 is also grounded, then V1 equal to V2 equal to 0. V output is designed as V1 minus V2 minus V1. Okay, so this also I should get A into 0 as 0. V output. Right, we should get this also as 0. Okay, now we should get this value as 0, but practically what happens is, in practice, okay, V output equal to 0, this is ideal case, but is you will get here plus 2 volts, okay, plus 2 volts practical. Okay, example, any voltage error you can get that we cannot predict, okay, that some voltage definitely there is a chance to get error, and that error if it is plus 2 volts here, okay, if that error is plus 2 volts here, then you will think that when there is no input I am getting output, it is a good result. Okay, why? Because it is advantage. Okay, suppose that without writing exams, if you pass the exams, okay, if you try to think like that, it is an advantage. Okay, in the similar manner, without giving input I am getting here output. So I think that it is advantage. It is not advantage, it is a disadvantage. Why? Because in your lab, when you try to take the record like this, okay, when these two inputs are 0, okay, you are supposed to get output 0. When you give some input, then you should get output as gain times this. Say the difference is 5 volts and the gain is 10. 5 into 10 I should get 50 volts. But in the lab when you do experiment, if you get extra 2 volts, okay, extra 2 volts, then definitely I will cross the, okay, answer. Why? Because you are getting wrong result. You are supposed to get 50, but you are getting 52. Okay, so it's not an advantage. So definitely it's an error. So don't think that without giving input, if I get output, it is a, okay, advantage. Sometimes we get an error. So you may get plus voltage or minus voltage also. There is a chance to get minus voltage also. Because of that reason, we should correct that. We correct this by connecting a voltage here like this. Okay, now connecting a voltage like this, because I am getting this voltage here like this, I connect this to inverting input terminal like this. So this is connected to ground. Now V2 is 0. Now I connect here this voltage, what I connected at input, this is called input offset voltage. Offset voltage. So I can say that here now V output will be equal to gain times, okay, now here I think that it is 0, but I am getting here plus. So 2 minus 2 should become here 2 minus 2, now it should become here 0. So we say that the voltage given at input, the voltage given at input to make output voltage 0 is called input offset voltage. I repeat, the voltage given at input to make the output voltage 0 is called input offset voltage. Now let us take break and resume back. Due to the offset values which I am speaking now, this op amp will quickly go to the saturation. At this situation, I'll have some output. That voltage will be given as input to this, and we are not giving any input, but this voltage gets amplified in this cycle. Now this circuit may fall into oscillations. Now for that we need to have some more additional network apart from that, which I consider it to be as nothing but positive feedback. So I can take it like this. So this is one of the few examples, but you need to wait for 2 more classes until I come to the positive feedback. Then you will understand it very clearly. Next, Neha, can you please do some questions on amplifier with RE and CE and some on with RE? Neha, let me put it here. We are a different topic. I cannot discuss that directly here. Because you will get one more topic with RE. Instead of RE, when we discuss FET, you will get RS with CS capacitor. That and BJT will be same. Once again, I will try to repeat, or else you can watch the video what I have explained with RE, and we'll do some problems on the feedback circuit also. Once I complete this part. So because the BJT and FET will be dealt at a time once again, and at that situation I'll try to explain it. Now only on feedback part. Next, Ashutosh from Bhilai. Sir, in case of difference amplifier in second diagram, the direction of IF is opposite. Why so? Now I think I have erased this part. Let me try to explain like this. So what do you mean by what you call second diagram? I don't know, but what I have written here, both circuits I'll try to draw, try to understand. Now here this is R1, now this is grounded. If it is an inverting amplifier, when input current comes like this, because of high input impedance, that is input resistance is infinity, then this current cannot enter into the op amp. So it will try to go, only way to go is like this. That is the reason I try to take it like this. This is the actual current flow, but conventional current flow we try to represent it like this. So here that is how we have taken it, nothing more than that. And next thing what we have here is the non-inverting amplifier. When you try to take, I try to give the input here like this. Now try to take here like this in case of non-inverting mode. I ground it here like this. Now what happens is here, the op amp is considered as a voltage amplifier. So what it will do is, no current will enter into this, but definitely this voltage will appear as input to this. And that voltage will appear in amplified form here, and that is fed back. So then I need to take from output here, because this is at higher potential, this is at lower potential. I take here IF feedback current like this, and this current, because no current can enter into this, the only way current has to enter, because of infinite input impedance, current cannot enter, current will come in this way. So this is how the current direction is taken. Now this is the point here. Now you can take the current direction any way as you want, but you need to satisfy the KCL and the potential difference. You should definitely satisfy it. In that way you can manage the directions, no problem. But most of the books are the way we understand is like this. Next, Aman from Delhi. How did you nullify the extra voltage? Please explain again. First let me know what is that nullify voltage. I got the question. That is the voltage what we give here. Fine. Now let me explain. So you try to understand here that in the offset voltages, let me re-explain this once again. When V1 and V2 voltages are 0, I should get output voltage 0, but practically I get here plus 2 volts. When I get plus 2 volts here practically, when I get here plus 2 volts practically, then what happens here is that I should understand that there must be some voltage at positive terminal only. Why? Because if there is at positive voltage plus terminal, then only I'll get output positive. if it is there at negative, okay, if the offset error voltage which is crept into the circuit into the IC at inverting terminal, I should get negative. So from this value what I get positive, I should understand that the error must be present at this plus terminal. So if it is present at the plus terminal, then definitely in order to nullify it, I should give it at the negative terminal. That is the reason I have given it to the negative terminal. So now what happens is, I need to take it here originally, that is 0. But what happened here, originally I should write this equation like this, that is 0 minus 2. Okay, I am giving the voltage here, so 0 minus 2. So then what happens is, I should get minus 2. But what is happening is, I thought that it is 0. But there is an error which I am not able to see. Due to that reason, that error I have identified it as some value 2. So 2 minus 2 is, I consider it to be 0. So now the output voltage will become 0. In this way I made it 0. Suppose you get output voltage minus 2 here, then I have to connect this voltage to this terminal, not to this terminal. This terminal I need to ground it. So first you need to identify what is the error voltage which you are getting at output. After identifying it, look at the polarity, whether it is plus or it is minus. If it is plus, you need to connect the offset value to negative terminal. If it is minus, you need to connect the offset value to positive terminal, so that the net voltage difference will be cancelled. Okay, this difference only, this is how we try to make output voltage 0. So by this we define that as the offset voltage, okay, input offset, the voltage given at input to make the output voltage 0 is called as input offset voltage. That is the point you need to understand. Now, so this is about input offset voltage. Now the next term what we have is, let us try to look here like this. Now suppose that here, when these two are grounded, now I need to have here IB1 here and IB2 here. Okay, now where you try to give inputs also, I need to have like this, V1 equal to V2, or you can take it as ground, okay, at this point. Now when you try to give the story here, what you have is, next one is input offset current. Input offset current. So if you try to take here, like this. Now these two are nothing but transistor base terminals which we have. Okay, so yesterday we have seen a differential emitter coupled differential amplifier. Okay, let us look at this part here. Emitter coupled differential amplifier. Now if you ground this terminal here, okay, no source, ground it, no source, ground it. Okay, like this. So then this must be 0, this must be 0, right? Now in practice, that is during the manufacturing using the VLSI technology, we design it and we fabricate it using some fabrication process. At that situation, these transistors must be identical. Okay, that is what we need to understand. The Q1, Q2 transistor must be identical. What do you mean by identical? It means it should have same H parameter values, it should have same beta factors, and everything should be same. Then only we can get it. But practically to get this value, it's very difficult. Okay, there will be a small difference between Q1 transistor and Q2 transistor. Always they are not same. So because there is a small difference between these two, what happens is that this current, when I provide here same voltage here, okay, now V1 here and V2 here like this, okay, when I provide same voltage here, then IB1 and IB2 are here like this. Okay, so V1 should be, V1 is equal to V2. If V1 is equal to V2, then okay, IB1 should be equal to IB2. IB1 should be equal to IB2, but they are not equal because the transistors are not identical. You will definitely get some difference between these 2 points. You will definitely get some difference between these 2 points. Okay, that is IB1 will be different from this IB2. Therefore, the difference in voltage, I call it as input offset voltage IIO, that is IB1 minus IB2. The difference of 2 base currents, what I get, okay, is called input offset current. Okay, we call this as input offset current. So the effect of difference in base currents, okay, all of you try to understand, the effect of difference in 2 base currents will reflect at output in voltage form. Okay, so you need to understand this point carefully. Okay, that is due to IIO, the error appears in output in voltage form. Okay, why? Because now you see here IB1 should be equal to IB2. Okay, but here IC1 will be equal to beta times, okay, IB1, okay, and IC2 is equal to beta times IB2. Because there is a difference in beta, or because there is a difference in any of the parameter of the transistor, due to that reason IC1 and IC2 will differ. If IB1 is equal to IB2 and beta 1 is equal to beta 2, then okay, IC1 should be equal to IC2. But in practice, okay, okay, IC1, okay, is IC1, IC2 minus IC1 is not equal to 0. Okay, is not equal to 0. Okay, if this is not equal to 0, then definitely I get here VC2 minus VC1 is also not equal to 0. Okay, I get some voltage definitely at the output. Okay, I get some voltage definitely at the output here. This is also not equal to 0. Okay, it means the error because of the base currents is reflecting at output in voltage form. Okay, the error at base currents is reflecting at the output in voltage form. So you can see here, this is here VC1 and this is here VC2. Now you can understand what is the importance of this base current. A small error created here that will reflect at the output, and definitely this current, these values will differ. Okay, so that is the point you need to understand. So because of that reason, now definitely you will find here a difference here. Okay, now at this point you carefully observe how to overcome this problem. Okay, that is how to overcome this input offset voltage. Okay, input offset current. How to overcome this? Okay, compensation. This is what we call compensation. Here, this op-amp plus minus, based on the error what you get, you need to connect one resistance here. This resistance is called as compensation here. So if you put a resistance here like this, okay, you will compensate the current input offset current, error due to input offset current appears at output in voltage form, that can be compensated here with the help of this resistance. Okay, because if you put a resistance here, that difference in current will develop some voltage here, okay, and that voltage will be nullified at the output, and net voltage you can get now V output equal to 0. So now what happens is that now because of this, okay, VC2 minus VC1 will become 0, okay, will become 0. So the output voltage, that is nothing but output voltage of op amp. This is nothing but V output voltage of op amp will become 0. Okay, this is how you can make the difference of these two circuit, okay, 0 here. Okay, fine. So this is about input offset current. So from this point you should understand here, okay, you should understand here that due to the error, or you can say mismatch in transistors, you call it as mismatch. Due to the mismatch in the transistor, the input offset voltage and input offset current will appear, okay, and this errors will appear in voltage form at output. So to make the output voltage 0, if you connect one voltage at input, it is called as input offset voltage. And to make the output voltage 0 due to errors in currents of input, we call this as input offset current. And that reflection, that overcoming that reflection, you can put it by putting a resistor at this point, you will be overcoming the drop. Okay, this is the point you need to understand. Now, so like this we try to do. And the important thing is, R compensation must be given only to plus terminal, not to the minus terminal. You should not give, because minus terminal will take care of the feedback here. You should not connect there. If you connect there, the error will not be solved. Now, so I am erasing this part. Now next we have input bias current. Let us look at this point, input bias current. Input bias current. Okay, now if you try to take here the input bias current, okay, like this, input bias current. Now how do we define input bias current? Is the average of, please take down the definition, the average of two input currents is called as input bias current. That is IIB is equal to IB1 plus IB2, okay, by 2. So this is called input bias current. The average of two base currents, okay, two input currents is called here IB1 plus IB2 by 2. So how do you understand this IB1 and IB2 is, when these two transistors are identical, then definitely the biasing conditions, that is nothing but biasing is for DC. You need to understand here. The word itself stands there, bias. Biasing is for DC. Okay, now the input voltage what you are giving here, the power supply what you are giving, will try to set up a base emitter conditions here and base emitter conditions here. So you can take the loop here and you can take the loop here. So this current will decide what is IB2 and IB1, which is going to maintain a voltage across this. Okay, and this base current what you have here and what you have here should be identical. Okay, if they are identical, then I try to take the total value equal. But in practice, because they are the two transistors due to mismatch, there exists some, okay, difference between IB2 and IB1. Then what you should understand is, one transistor may try to draw more base current than it is required. So then power dissipation in that particular transistor across the resistors will be more. So therefore, there may be, quick consumption of the VCC. Why? Because it is trying to draw more current than the expected value. So your mathematical calculation, you make it before manufacturing the device, but after manufacturing, due to the mismatch in the transistors, the biasing currents will differ. Then what happens is that you will not have exact value as expected by what you have calculated mathematically, that will not meet the practical value. So due to that reason, power dissipation will be more, okay, due to the DC values at the resistors. Okay, so instead of taking them equal, what we do is we try to take sum of these two and calculate average. Then only you will get actual power consumption done by base current, okay, for the biasing. Okay, so that is the reason we try to take like this. So I repeat the definition. That is, the average of two base currents is called as input bias current. Okay, we call it as input bias current. The average of two base currents is called as input bias current. So you can take it like this. Okay. Input bias current. Input bias current. Now everybody try to see the next one we have, that is output to offset voltage. Out of all, this is the most important and best, what do you call, important point out of all these things. Now fourth one you consider here like this: output offset voltage. This is important out of all offset values. Okay, output offset voltage. Okay, now so let us try to see here what is this output offset voltage. Now try to take like this, minus plus, I have output. Now say that you have connected one source like this, 2 volts, okay, and grounded it, and because you got error, you have connected one input offset, okay, we call this as input offset voltage, right? To overcome the input offset voltage and make output voltage 0, you have connected one voltage source at input. I call this as input offset voltage. And to overcome the input offset current, you have connected one resistor here, R compensation at this point. Okay, for the sake of, okay, for input offset current. Input offset current. Okay, now this both are existing because of mismatch in the transistors, okay, while manufacturing. To overcome these two, you have given it. But now what will happen is that, okay, because you have added an additional voltage here, this voltage will interfere with the input signals what you are giving. Okay, I have grounded here, but if you try to give input signal, then this resistor and this voltage will create some effect on input values, and again once again output will become an error. Okay, so if you carefully observe, to correct the errors, you have given compensation. By giving compensation, a new error will arise because these values may not exactly satisfy the input signals what you give. So when you combine the input signals V1 and V2 with this error word compensation values, you will get some new error, okay, which may not match exactly. That is the reason you will get once again error. So already input and offset voltage and input offset current are nothing but error. Correction. To correct that, if you have done some job and that job has created another new problem and it is giving once again new error. So now it's really a fed up job with the op amp if you try to keep on correcting like this. That is the reason they made it more simple, okay, and given us here, that is output offset voltage. Now please everybody try to see here. This is pin number 5. Pin number here minus V supply, and I have here this voltage like this. Okay, now what I try to do is, using this power supply, what I try to do is I'll put here one potentiometer like this, minus VEE. I'll put some potentiometer here like this and connect this to pin 5, okay, from the output. Now what happens is, let there be 100 errors, now we don't bother, okay, let there be 100 errors, we don't bother about it. If I get, okay, any error voltage here, I'll try to take the supply from this potentiometer here connected to pin number 5 and readjust this here. Okay, once I readjust it, whatever output voltage you get here, that will be nullified and made to 0. So we consider now this, we define this output offset voltage as the voltage given at output to make the the voltage given at output to make the output voltage 0. We call it as output offset voltage. So you can take it like this: the voltage given at output, okay, to make the output voltage 0, okay, is called output offset voltage. You call this as output offset voltage. Now I repeat, the voltage given at output to make the output voltage 0, okay, is called output offset voltage. Now an important point, so that is note, you need to note there, the output offset voltage, okay, is due to, the output offset voltage is due to, okay, the mismatch in transistors and input offset voltage and input offset current compensations input offset voltage compensation. So like this we try to go. Now let there be new error also, we don't bother now. Why? Because whatever error comes, if I get error voltage here, I can just nullify it with the help of this pin, okay, connected to the power supply. Whatever voltage comes, you need to get here the value 0, okay. That is the use or provision provided by the op amp as pin number offset values, okay, for offset values. Now this completes DC characteristics. So for a DC characteristics means we need not worry about anything about internal biasing. We need to only do one job, find out the errors and correct them, okay, due to the DC functions what you have. That's it. Now we are supposed to study here AC characteristics, okay. Now so let us try to study here AC characteristics of the op amp. Okay, AC characteristics. Now look at this. Now look at this AC characteristics. That is, we have studied AC characteristics means when I try to provide AC input signal to the op-amp, okay, then it is supposed to amplify that AC signal and present it at the output. Okay, wonderfully it will do it, no problem. Okay, but that AC signal, when I say AC signal, it will definitely have some frequency. It will definitely have some frequency, and that frequency what we give, okay, that frequency what we give is definitely will make an impact on the performance or the gain of the op-amp. Okay, why? Because the op-amp inside it always has the same transistors what we have studied earlier. So at high frequencies, the transistors which are present will lose their property of amplification because of poor reactance provided by the stray capacitance. Okay, you can understand that under forward bias, a resistor will have, a PN junction will have forward resistance RBE. Okay, you can name it, and you can under reverse bias, I say RBC, right, like this. Now, under forward bias, a PN junction will exhibit a capacitance called CBE, and reverse bias, it will exhibit a transition capacitance called CBC. Now, these are the frequencies, but we know that X C equal to 1 by 2 pi Fc, capacitive reactance. So when frequency is very high, say for example infinity, then Xc will become 0. So then this transistor at high frequencies, okay, or mid frequencies also you can take, okay, what happens is it will lose its properties of amplification. Why? Because even though you have here resistance forward and resistance, now these capacitors will act as short circuit. Now what happens is that whatever input signal you give here, IE, that is IE, okay, direct here, this current is going to come like this directly. No amplification, okay, no amplification, because at high frequencies the capacitor will act as short circuit. Okay, the transfer of resistance characteristics, is lost by the transistor, because the emitter base junction low resistance what you experience will become too low, and the high resistance between collector base junction because of reverse bias that also becomes low. Now, so both areas you will have low resistance, transistor is acting as a short circuit. The truth is that the DC conditions show that the transistor is in active region, but the transistor will not provide you any amplification. Instead, it will provide you, okay, zero gain. Why? Because how much you give, same thing will appear at the output. Now the transfer function, if you try to write V0 by Vi for AC, you will get 1, nothing, no amplification. As it is, the signal will appear. Okay, and this part, when you try to observe like this, because I am losing the gain factor here, now I say no more transistor is a amplifier. Okay, these are the transistors, same transistors we use in the op-amp also. Excuse me. That is the reason we should study this. Now, how to overcome this problem? Okay, we can overcome this problem by compensation technique, that is by putting a capacitor, okay, where the reactance is going to become 0. Okay, where the reactance is going to become 0. So if you provide sufficient reactance, okay, then externally, if you provide some capacitors to the op-amp, then it can hold the voltage. It will not make it 0. Okay, that we try to study it like this. Now, so AC characteristics is also called here as gain frequency response. Okay, this is nothing but we call it as gain frequency response. Gain frequency response. Let us try to take it like this. Now, an op-amp has got the input here V1, V2, equivalent circuit. This is RI and this is here VD I have. and the equivalent circuit I take it like this, AV into VD, and R0 here for the op amp, nothing but Thevenin circuit, R0, it is a voltage amplifier circuit. Now I have. So consider this to be the equivalent circuit of op amp. At this situation, what I try to do is, to the output of op amp, I connect one capacitor here. This is how I am supposed to take output. I connect one what you call capacitor to this. Okay, that is where, because the capacitor reactance is becoming 0, externally we try to connect one capacitor to the op amp and try to compensate this. Okay, and overcome this problem. Now try to see here like this. V output, you have it like this. So V output is nothing but current in this loop. If I consider it I0 into minus what you call capacitor to this. Okay, that is where, because the capacitor reactance is becoming 0, externally we try to connect one capacitor to the op amp and try to compensate this. Okay, and overcome this problem. Now try to see here like this. V output, you have it like this. So V output is nothing but current in this loop. If I consider it I0 into minus JXC. Okay, this is what I get. So V0 into I0 is nothing but AV into VD divided by R minus R0 minus JXC. Okay, into minus JXC. Right, now I consider it like this. Okay, you can consider this as A into VD, convenience, A into VD. Now I have here like this. Now A into VD, I bring it this side. Now divide both numerator and denominator with minus JXC. Divide with minus JXC. Okay. So on dividing this with minus JXC, you get this as 1 plus R0 divided by, okay, minus JXC. This is what you get. Now V0 by VD is nothing but gain. Okay. After connecting the capacitor, V0 by VD is the gain. Without capacitor, this is the gain of the op amp. So AV equal to A divided by 1 plus, I will move the J up, okay, and XC is 1 by 2 pi FC. So 2 pi F, okay, C, 2 pi FC into R0. So I will rearrange this equation like this. V output equal to A divided by 1 plus J, F by F, okay, FH, where here FH will be equal to 1 by 2 pi R0 C. Okay, this is the point you need to remember. Okay, now, so now this is the formula for the voltage gain and frequency response. So magnitude, if I try to take, I get this A divided by square root of 1 plus F by FH whole square. Okay, now using this, we'll try to understand the response of AC signals for an op-amp. Now, frequency FH is called cutoff frequency. So, we call this as cutoff frequency. Cutoff frequency tells us, cutoff frequency tells us the limit of operation, up to which you will have gain, normally or constant. Now, you can understand this point very carefully like this. Everybody try to see. This is the most important point, Try to see here like this, gain A and F. Now please try to see here that I'll try to substitute the values here for this. Now for F is equal to, F is a variable factor. You can see here, everybody, F is a variable factor. F has got freedom to change, from 0 to infinity. F can go from 0 to infinity. Now, but FH is cutoff frequency. It will show the limit. Beyond this, if you go, your gain will fall down. That is what it shows. So, F is equal to FH. F is equal to 0. You put it. Then if you put F is equal to 0, 1 plus 0 is A. So, I have very good gain. Full gain I am getting here. Gain here. The gain AV. So, full gain I am getting it here. Like this. Now, if F is increased, then here AV is equal to A. So, if F is equal to FH at cutoff frequency, then I get AV equal to A by root 2. So, root 2 value is 0.707. This is how I get 0.707. Now, if F is increased to, infinity, then if F is infinity, 1 by anything, infinity by anything is infinity. 1 plus infinity is infinity. Infinity. 1 by infinity is 0. So, it means now AV value will become 0. AV value will become 0. So, from this point, one can understand it like this. So, the gain is going to fall down. It is supposed to fall ideally, perfectly like this, but it doesn't fall at that point. So, this is FH and the value at this point will be 0.707. If you convert this into decibels, then I get it here as minus 3 dB because gain is falling down. This is here FH. Now bandwidth of this circuit, if you try to take bandwidth is equal to FH minus 0. So FH itself is bandwidth here. FH itself is bandwidth here. Now this falling, we call it as gain starts falling as you increase frequency, and this fall in gain we call it as roll off rate. We call the fall in gain as roll off rate, and if it is of first order, say one capacitor you use, it is minus 20 dB per decade. So for every 10 times increase in frequency, roll off rate, you call it as roll off rate. That is the gain, that is the gain will be falling, at minus 20 dB per decade. It means whenever you try to increase the frequency 10 times, from 10 Hz to 100 Hz, then the 10 times you have increased the frequency, input signal frequency, so gain falls at minus 20 dB. If you go from 100 to 1000, 10 times, gain falls with minus 40 dB, and 1000 to 10,000, it falls at minus 60 dB. 10,000 to 1 lakh, it falls at minus 80 dB. It means the gain is going to fall down like this. This is what it is, the response. So this is the roll off rate. You can get it like this, you can get it like this, you can get it like this. So high roll off rate, minus 80 dB per decade. 80 dB per decade. So this is 80 dB, and here this is minus 20 dB per decade. So like this, the fall of gain is called as roll-off rate, and if more the roll-off rate you have, you will try to get an ideal condition. But there are additional problems with that. Why? Because gain also, bandwidth will be changed. Okay, bandwidth will be changed. Bandwidth will not become constant, because gain bandwidth product is always constant. That is the reason you will not get both at a time. What is it? We'll see now. What is gain bandwidth product? We'll see. So time being, try to remember here this point. Okay, so this is about the frequency response or gain frequency response or AC characteristics of the op-amp. So op-amp is working as an amplifier. When it works as an amplifier, if you are between 0 and FH, it gives you excellent gain, no problem. But if you cross FH, the gain of the op-amp is going to fall down. Then it tells us that this is a good op-amp up to 100 kilohertz, 150 kilohertz, 1000 kilohertz. It will mention what is FH. Okay, that cutoff frequency will mention within this range it is excellent. But if you cross the range, then the gain of the frequency will fall down. Okay, that is why I told you in ideal conditions. Okay, in ideal conditions I told you that the op-amp, okay, that is the op-amp is not, we cannot meet ideal condition infinite bandwidth in practice. Okay, so we just study it as an ideal condition at that point. Fine. So this is about the roll-off rate, okay, and gain frequency response. Or AC characteristics of a op-amp. Okay, let us try to see here the important point next to this. I'm erasing this part. Now let us try to see here some of the important parameters here for this. Now I'm erasing this part. Now important parameters for this, let us try to see here. That is, the important parameters what we have here is, first one, CMRR, common mode rejection ratio, and we have slew rate, and we have next gain bandwidth product. Gain bandwidth product. Okay, so these are the most important features of the op-amp. Whenever you select a op-amp, we try to look at these two factors, CMRR and slew rate, and next we look at the gain bandwidth product. By observing these three important characteristics of the op-amp, okay, we consider the op-amp, okay, whether it is good or not. That is important parameters. Okay, important parameters of op-amp. How you study that it is a good op-amp or not? Okay, these are the important parameters. So let us look here. First one, CMRR. Okay, CMRR, common mode rejection ratio. Common mode rejection ratio. The CMRR is defined as ratio of difference mode gain to common mode gain. Okay, ratio of difference mode gain to common mode gain. What do you mean by ratio of difference mode gain to common mode gain? Okay. Now, what do you mean by this? So, that this part, if you try to see here, AD by AC, when you try to take here, difference mode gain to common mode gain, okay, we understand it like this. An op-amp definition is, it is supposed to amplify the difference of two input signals. That is how, or that is the purpose of design of the op-amp. But what it will do is, the op-amp terminals doesn't know what is input, what is noise signal, because the noise and voltage, noise signal also appears in voltage or current form only. So what happens under such conditions? What happens at that situation is, if this difference, okay, now what happens at that situation is, this difference what you try to see here, okay, AD, okay, and this should be very high and common mode signal should be 0, because noise will enter to both the terminals in common. When they enter, when both stages are equal, if you give two equal inputs to the op-amp, as per if it is working as an excellent difference amplifier, then the difference of these two should become 0. Then the difference of these two should become 0. So you should find out the difference of these two 0. But what happens practically is that, okay, if this op-amp is amplifying the noise signal also simultaneously, then we say that common mode gain is high. Okay, when the common mode gain is high, then what will happen here is that, okay, you will not be able to get this this op-amp work as a differential amplifier, because its gain factor will be reduced. So now you should remember like this, that is, an op-amp should work as a good differential amplifier, and it should not allow common mode gain. But in practice we cannot avoid it. Noise will definitely be common to both terminals. That also will get amplified and appear at the output. So you will definitely get some common mode gain also for an op-amp. So you should see that ideally we should have infinite CMRR. Why? Because, okay, ideally, okay, op-amp should have okay, AD very high, okay, very high, and AC 0, but practically it is not possible. You will definitely have some AC. Due to that reason, we say, okay, the CMRR is equal to, okay, CMRR should be infinity ideally. That is possible only when this condition is satisfied. Okay, very high practically. Very high practically. Now, how do you get this in sense? The AD value is given like this. AD is equal to V output by VD. That is nothing but V output by modulus of V1 minus V2. But AC is given like this. V output by VC. That is given here as VC is nothing but noise signal or common mode signal, which I consider it as average of two input signals. V1 plus V2 by 2. Okay, V1 plus V2 by 2. So this here is a unwanted signal. It should be, so which will enter. We don't know how much it exactly enters because it's a noise. Okay, it's a random signal. So we try to take average of the two inputs entered as a noise signal into the op-amp. And write this as V1 plus V2 by 2. So when you try to write like this, this is what we call it as common mode signal, and this we consider it as difference mode signal. When you take the ratio, so CMRR is defined as the ratio of Okay, the ratio of CMRR is defined as the ratio of the difference mode gain to common mode gain is called, okay, CMRR. The ratio of difference mode gain to common mode gain is called CMRR. Okay, the ratio of difference mode gain to common mode gain. Fine. So this is about the CMRR you have, and you can have it. The next one you have is slew rate. Now copy this quickly. Right. I'm erasing this part. Now next you have slew rate here. The second one, slew rate. Now you try to see here, this is a very, very important term. The slew rate is defined as the ratio. This is defined as the ratio of change in output voltage